The derivation sheet serves as the essential mathematical anchor for both the state and sequence diagrams, providing the formal proof that these coordinate systems are built on perfect 90-degree angles. Relationship with the state diagram. The state diagram uses the conclusions of the derivation sheet as its foundational starting point. While the derivation sheet provides the static proof of coordinate independence, the state diagram maps out how this core truth transitions into dynamic real-world applications. It shows that the verified math from the sheet is what powers three specific visual demonstrations. Robot motion. The proof from the derivation sheet ensures that as a robot moves, its directional arrows always stay perpendicular, allowing the system to track its path accurately. Atomic structure. The same proof allows the state diagram to transition into physics, showing how an atom's complex shape can be broken down into independent shells and lobes. Relationship with the sequence diagram. The sequence diagram illustrates the logical handoff of information that begins with the derivation sheet's verification process. It depicts a step-by-step story, where the mathematical proof is the trigger for all subsequent efficiency. The handoff. Once the derivation sheet confirms the coordinates are perpendicular, this information is sent to control systems and physics solvers. The result. The sequence diagram shows that because of the work done in the derivation sheet, the robotic system can calculate movements much faster and the physics system can solve atomic equations without different dimensions getting tangled or interfering with each other. Summary of the connection. In short, the derivation sheet provides the theoretical engine, while the two diagrams illustrate the vehicle and its destination. Without the specific geometric relationship proven in the sheet, the computational speed in robotics and the structural clarity in atomic theory would be mathematically impossible.